I wanted to ask our experts what you think are the next challenges and trends in AI. And I would start with Tobias, maybe, and then we just go around.
Yeah, very good. So I can start a little bit with emphasizing or connecting to a point where Michael closed his talk in recommending and helping the user to find insights in visualization using machine learning. So that's a great application opportunity in my opinion. So you talked about quality measures, and I think this is a first step, and we can go much further by supporting users in specific tasks, offering them appropriate visualizations or further on appropriate models to solve their tasks, and this is very complex because there are so many tasks to support. And this is from the user perspective for interactive data exploration, for example, one of the key application opportunities I see, to bring in machine learning to help the exploration process, by not leaving the user like drowning in data or drowning in views and parameters, but suggesting good steps.
Yeah, thank you. Michael.
Agree. Next one. No. So of course I fully agree, but maybe I make a different point than here. I think also fully agree on human plus machine interaction. That's basically the topic of my talk. But so I want to pick up on a topic that Volker mentioned in his first talk, because he's not here, which is this notion of like a data scientist and you need to learn all the skills, which I think is impossible. So you're gonna be an expert in everything. That's just like not gonna happen. So I think like we need to build these infrastructure to foster collaboration. So in fact, this is also some work that we have done already 10 years ago, like setting up a methodology, a human-centered methodology to run these projects, including domain experts, but also visualization experts, data experts. And I think this is gonna be a great challenge. And of course, not to speak of like, general solutions for human data interaction, but I talked about that earlier.
Well, it sounds like a cool approach, yes.
Yeah, so I guess I'd focus more, my personal bias being towards the machine learning research side. I think that a really exciting area that we're research that we're seeing arise is the intersection of causality and machine learning. Right now, basically, I think there's a criticism of current machine learning approaches, most of them being very correlation based. It's just statistical correlations that we're extracting from data, which we're quite good at this now, but we're not learning models that seem to have a causal understanding of the world. And so I think that this will be a major area of research, and hopefully a very fruitful way to push AI and machine learning and data science forward.
Okay, so we have challenges. So we have this huge incentive to collect data because that helps us in general. Of course, there's counter examples, but in general, big amounts of data help us to improve machine learning systems. The trouble is that often these data collections, they pose a risk by themselves as well, and that's where this protection encryption technologies, what Dimitar was talking about today, is something that will be more and more needed in the future, except that it slows things down. We cannot apply it everywhere, especially at very large scale. So that's something I see as a big challenge, even as an obstacle to move forward, because at some point society will say, wait a bit, stop, this is going to be too dangerous, perhaps, especially when we talk about personal information. A second thing is that if you're not exactly Google, you may benefit a lot from sharing data with many others, because you don't have so much data. But then there may be competitive reasons why you actually have a disincentive to share, because you don't want to give your competitors an advantage just because you open up your data. But then there would be methods that would allow to benefit from such an outcome of a sharing without actually exposing your data to the public. And again, these methods we know they exist. There are niche applications where these niches are getting bigger and bigger. These work already, but there's a lot more to be done to make them really scale for even larger data sets.
So that actually means that data science needs to become much more collaborative. So on the one hand, bringing together all these different expertises of different data scientist types together with different kinds of machine learning and causality with different kinds of data, or with sharing the data as well, right? Just trying to connect things a little bit. Okay.
We have to talk to each other more in the future. That's
that always helps. Dimitri.
So, thank you. So I would go back to something that both Ian and Christian said. For me, obviously, the main challenge is making sure that the machine learning community and the cryptographic community converge into these areas. So there's no doubt that a machine learning model can benefit from having external data or data that you share. However, this data cannot really be given to you in plain text. So that's one of the challenges. And then making sure that this can be computed in an environment that is scalable, that's easy to use by the machine learning community without actually exposing any of the underlying cryptography. So that's one of the goals. Now talking about causality and what Ian was talking about earlier today. So the typical example is that you have a model that you build in-house, and then you have out there a data source that you don't see. How do you actually test the quality of this data source in improving your model? So you could actually use some of these privacy-preserving techniques to compute some causality statistics. So we did this with banks before, and so that could give you really qualitative information about the quality of the external data source. So I think this type of collaboration needs to converge a lot more. And also from the ML community, what's important to understand is that privacy-preserving computing, they have limitations, so you can't do everything there.
Yeah, so that's the first point of use was, I think, a very good lead over to Matthias. So
I would actually like to answer this a little more general. So first of all, make an observation. So what you actually see across many different research communities is this classical ML for systems for ML, pretty much this bi-directional usage that we're trying to build systems for machine learning workloads, and at the same time, we try to apply just existing models to do replace all sorts of tuning knobs in our own systems that are currently just heuristics. So Google and kind of MIT started with that, ML for systems for ML. Today we've seen ML for Wiz for ML, and this is exactly the same in programming languages and various other fields, and now we see it in cryptography as well. So I think that's a general trend. It's currently a bar, so probably at the peak. It will go down a little bit, but I think it's actually very useful to think in a bi-directional manner and see what are the commonalities across different research communities. And that brings me to what I believe is actually the trend and the challenge that we are facing. And for me, it boils down to two meta concepts. One is abstraction, and the second is specialization. So when talking to Tobias and Craig already, we've seen that actually we are all trying to build the same things. We are all trying to build some form of abstractions from our perspective. So for Tobias, it's kind of how the user interacts with the UI. For me, it's kind of what are the built-in functions we're supporting for different kind of steps in the entire data science lifecycle. Here it's about the back end that you try to hide from the user. And under the covers, you try to specialize. And you see that across the entire stack, all the way down to the hardware, in order to provide actual scaling, you specialize. You specialize for a particular model and try to be more efficient with the resources that you have.
what about specialization for a specific domain? So this main question for me is like, what's with prior knowledge? So I still don't totally buy it that we will be able to find all the insights just bottom up. So.
Absolutely. So that's exactly. So I agree with you. Absolutely. I think it goes throughout the entire stack. For me, domain expertise and applications are at the top of the stack. And
I mean, when we are talking to our industrial partners, that's exactly the problem we are seeing, that it takes a month of a data science project to discover some relationship between two physical kind of properties that are known from the beginning for somebody who actually knew the domain. And of course, you don't want to waste your time and kind of combine the two things. And I mean, there are approaches that try to combine kind of rules and machine learning in a larger system that allows some form of kind of constraints on and kind of guarantees about the model that you are having.
Okay, maybe Dimitra, if we go the other way around now. So maybe also for you the question about the prior knowledge thing. How can we include this more in the future ML systems? And on the other hand, what about specialized hardware, AI hardware?
AI hardware, that's a great question. Yes, so you by saying prior knowledge, you really mean knowledge that we have acquired in the. So could you?
Whatever physical knowledge, chemical knowledge, what we know in the application domains, that we know these kind of chemicals react in a certain way, or whatever, all these kind of correlations which we could also come up with through the data, but which we know in advance and which could help us.
Yes, I mean, of course, that's kind of been a process in the development of machine learning also. And also, like a lot of these, I would say that, especially now, in my field, which is privacy-preserving computations, it's really important that you think about algorithms at a very low level. So even simple algorithms that you're used to computing in data-dependent way on plain text data, they never work on data that you don't see. So you have to start thinking very fundamentally of how I could design novel data-independent algorithms. And then you go back to actual prior knowledge. So all of these ideas from mathematics, and also some of them having physical intuition, like data-independent optimization algorithms. I think that is really something that would become the interface of the two areas that could help the ML community, that could help also the cryptographic community. So now the question about specialized hardware, I'm a strong believer that could help. We have to understand like what is our tolerance to trusting special hardware, of course, for what operations we would like to trust, for what operations we would like to trust mathematics and cryptography and the mathematical paradoxes. So I think at the end of the day, it's going to be like a combination of the two that would.
What kind of hardware are you thinking of?
So, like Ian asked me a question about SGX, but also, as I mentioned in my talk, using hardware to accelerate some of these computations, even in plain text. So understanding how to write proper algorithms for these hardware accelerators, I think that's already a very challenging task.
Yeah, I essentially agree with you, Dimitar. Perhaps a few smaller things to add about trusting hardware like SGX. That's what we had as a question here. So just next to my office, there are guys breaking SGX every few months and making global headlines all the time. And this doesn't happen so often with fundamental crypto assumptions. In that case, I tend to trust the crypto more than the trusted hardware. Of course, you would hope that finally perhaps even trusted hardware is stabilizing as well, and then we indeed can make things much more efficient. That would help, definitely. Yeah. On the other hand, actually, here locally, with NXP, we have a collaborator partner who is putting machine learning accelerators on edge computing devices, and that's something I think there's definitely a need, and there's more to be done.
So, but what happens now if we have quantum computers? What happens then with your encryption?
Not too much, probably. Not too much. It's our job to make sure that indeed not too much happens, but I think we are doing our homework, and even it may take a few decades anyhow to have stable, large-scale quantum computers. That would be a threat for some systems, but I think we are in good shape to not run into troubles once they are there.
Ian, what's your point of view on these questions? AI hardware and prior knowledge.
Yeah, they're both important questions. I think that, like, incorporating prior knowledge, like incorporating knowledge graph type things into machine learning it's a really challenging research problem still. I don't know that I have any particular insight onto how that will be solved, but that's actually like after the causality thing, that was my second choice for like the most important challenges for the field. To offer a slightly different perspective on the hardware question, there's I think people talk about this to some extent now, but doing machine learning is incredibly energy intensive. And so the specialized hardware I view for like accelerators, part of the importance of like making better specialized hardware for machine learning is to like stop global warming type consequences. When you think about as a machine learning researcher how much energy you actually consume relative to the like average, even like average American citizen, it's a lot more when you're running on these accelerators all the time. They use a lot of power. So I think that there's just from kind of being a good global citizen perspective, you really do need to figure out how to do these computations, do this training in an energy efficient manner.
Or at least use the servers to heat our houses or something like that as well.
Okay, so as an HCI researcher, I'm not commenting on the hardware. You guys got that? But the prior knowledge. So I want to start a little bit historically, because this is not a new notion in HCI, neither in visualization. And so we're not thinking of that as a sort of Bayesian framework here, but really how to incorporate domain knowledge into our tools. So in the 90s, there was this saying that people said, if you build a tool for a medical doctor, it should be usable by the medical doctor, not by the computer scientists, which was the case back then. And I see something similar happening now here, right? So in visualization, there's also a history. There was this huge push towards visual analytics, after 9/11. In the States. And the idea was to bring domain scientists together with statisticians and computer scientists. So in some ways I would say this is like a precursor to what we're doing in data science now, right? And for some reason, people went off and did very specific projects, but now we're seeing that again. So, but again, I think we're mostly focusing on ourselves here, right? We're building tools for computer scientists. That's why it works so great at Google, right? We're eating our own dog food. That's great. But we're sort of ignoring all this knowledge that these domain experts have. And I think it's a little bit arrogant to say that we can just model everything, right? There's all this tacit knowledge. There's all this lifelong experience that these people have. And so that's why I argue for human-computer interaction. Those people should work together. And now, of course, we could argue, well, in 10 years we have everything in a computer, but the world changes. And these people will change. The tools will change them. But there will be tacit knowledge again. So that's a moving target. Okay?
Okay. That comes actually to my...
Sorry, do I get protection to get out here?
No, actually, this leads me directly to my next
the back
question.
Door. Okay, good.
So, how will this AI thing change our society within the next 10 years?
Yes, it will.
How?
Well, it's so should we?
Oh, you can also talk about it.
Okay, so maybe quickly. So yes, it will change, but technology always has changed the world. I still remember. So Volker also mentioned data scientists being the most sexiest job of the 21st century. I still remember Friends, right? This one guy, he was actually a data scientist. He was a stats person. That was the uncoolest thing in the 90s ever. Right? Life changes. Okay, that aside, technology changes people, so I think we will see a lot of things that is done manually now or semi-automatically now, shifting to what's more automation, like self-driving cars, in medicine, supporting people, doctors with computational AI methods, but also other computational methods, in law, lawyers, there's all this notion of data-driven decision-making that's just great. So that will change, of course, the world, but the people also will change with that and use these new tools.
So it's more IA, intelligent assistants instead of AI.
Yeah, yeah. Or immersive analytics, but that's a different thing.
Yeah, thanks. So many interesting points to discuss. I will only quickly comment a bit on prior knowledge. So also not on hardware, but on like approaches that we can implement to help the interactive data exploration process in visualization and in data analysis. So in our community, in visual analytics, there is in InfoVis, there is a trend to include analytical provenance into the systems, which actually capture what the users are doing when exploring data with visualizations, like when they choose certain views, when they circle or mark something as interesting, when they do an export. And I think this is a huge potential to further develop our visual analytics systems, or data analytics systems, to be a bit more sensitive what users are doing with the system, capturing that, and that offers lots of improvement potential. For example, doing recommendations for future users based on previous knowledge, and that is over time that the exploratory systems can gather knowledge about how data is used, how views are used, how interaction proceeds, and therefore over time the system could gather knowledge to that respect. On the other hand, what we see in research is coming back also to the notion of quality measures, how to predict whether a view on data is interesting. We see some research groups doing annotations of views in the order of about tens of thousands of views, for example in scatter plots. And it's interesting to see whether that's already sufficient to train a model that includes prior knowledge of when a scatter plot is interesting or contains non-trivial information. Maybe we need 100,000 examples or millions of examples. I don't know, maybe with crowdsourcing we can provide more training to eventually arrive at prior knowledge or interestingness of visualization. So it was, I guess, a lot on prior knowledge here, and a bit on the change on society. I think, also we can expect lots of things. What I would personally like to see is to enable access to more people, to casual users, to use the potential of machine learning approaches, and maybe we can get even better in integrating interactive visualization systems with machine learning backends in order to bring analytical potential to a much larger user base. That would be my wish.
Democratize machine learning.
Yes.
Well, I think we computer scientists have been pretty good in automating a lot of stuff all the time and always finding something new to do, right? But with this, I would like to thank the panel very much. Thanks for coming up here, discussing with us. And there are still a lot of people out there for discussions. And with this, I would like to go towards the challenge, right?